Hello everyone, and welcome to my presentation. My name is Joe Alexandersen, and I'm an assistant professor at the University of Southern Denmark. And today I'll be talking about the application of full and approximate flow models in topology optimization of passive cooling for electronics cabinets. So my research focuses on simulation-based design optimization. So that's where we combine simulations with gradient information and mathematical programming to provide a simulation-based design optimization method. Topology optimization is an iterative method that aims to determine whether each point in space should be solid or not. It's an iterative process where multiple simulations are carried out in between design updates. The design parameterization for flow is that we have the ordinary Navier-Stokes flow, and then we add this Brinkmann penalty term that for a true solid should be infinite, so we get zero velocities inside. However, in practice, we have an upper bound for this penalization term that should be larger than 1 in order to ensure small velocities. So we have 0, gamma equals 0 is pure fluid, gamma equals 1 is pure solid, and then we have something in between. If you want to know more information, we recently published a review paper on the topology optimization for flow-based problems, so you can find all the papers that you need in there. So generally for heat sinks, which is what I've primarily worked with, we have these very simple geometries here. So we have pin fins, straight fins, and maybe these slanted fins as well. We also have more complicated contraptions that are composites of these, but true to all of these are relatively simple geometries and very cheap to manufacture. And they are generally quite applicable to a range of situations. However, the question is, can we optimize these heat sinks for a particular application and then win quite a lot in performance? And it turns out topology optimization is such a tool. So I've primarily worked with natural convection, so that's passive cooling, and we see here two of the applications I will talk about. So LED lamps and electronics cooling. So our paper from 2016 demonstrated this large-scale framework for optimizing three-dimensional natural convection problems. So here we have our problem is this enclosure here. We have a heat source at the center middle here, which can illustrate an electronics chip. And then we have a gray domain on top here. That's where we can place our solid material inside the fluid domain. And here we of course have not only the fluid equations, but also the conjugate heat transfer equations. So we're also determining where to place the highly conductive material and where to place the low conductive but convective fluid. And we see as we increase the Grashof number from left to right, so that's increasing the importance of natural convection, we go from these long, slender, straight members here, and they sort of start to curl up and contract. We get more and more complicated structures here, but we also see that we get these vertical surface areas that are of course there to accelerate the flow, but also to increase the surface area parallel to the flow, which increases heat transfer. But the point is, these are very big computations, so it takes around 10 hours to optimize on 1280 cores, so it takes a long time. But of course, we do get significant improvements in performance compared to traditional heat sinks. The next project I worked on was passive coolers for LED lamps. So we worked together with an industrial design company where they wanted to integrate the passive cooler into the design of the lamp, as we see here. They were very fond of these lattice type heat sinks because they were self-supportive, so they were able to 3D print these very intricate structures, but they also wanted to see whether they were able to do better, and that's where we tried to apply topology optimization. So we used topology optimization for this problem. We got 3 different designs. These 2 are for a horizontal orientation, so the light source shining this way, which will be clear from a figure on the next slide. this is pointing vertically downwards, so the light source is going straight down. We also have two different degrees of symmetry. This just has one symmetry plane, this has four. We get different designs for the different cases, but they share similar characteristics. So again, we see these elongated cross sections that are important both to guide and accelerate the flow, but also to improve or increase the surface area and contacts with the fluid. But more importantly, they all have a cavity in the center. And this is quite unlike what I've seen for most heat sinks for this type of application. And these give less flow resistance and more acceleration, but also have a thermal purpose, which I'll discuss on the next slide. But again, these are big problems taking several days on a small supercomputer here. So these are quite tough problems still to solve. So thermally, these open cross sections are very important because, as you see for the lattice type structure, the air quickly gets warmed up as it passes through the heatsink. So therefore the heat transfer is much more inefficient here on the top members. Whereas these open designs, they allow cool air to reach the members at the top, either by being drawn up directly here or from the sides. And they also are important with respect to flow resistance. So for the lattice here, we see a lot of stagnation pressure regions due to the high flow resistance. And here we actually see a negative pressure region, which helps accelerate the flow and increasing heat transfer for the top members again. So like I said, these are very expensive computations. Right now we need supercomputers to solve these. So that's not, it's doable in an academic context, but of course we want this to be usable in an industrial context. And we want to go to this solution, maybe not quite as fast as the animation shows here, but we want to have the engineers sitting relatively interactive, maybe during the workday. You can see how your heatsink design progresses. You can maybe change some boundary conditions or some settings, and then you can see how the design changes during your workday or maybe overnight. And we recently introduced a simplified model that is capable of reducing the computational time quite significantly. So what we do is we take again the Navier-Stokes equations here with a Bisque approximation. We simplify it to what becomes like a potential flow model here. So we have this fictitious viscosity-like term that is not a viscosity, but we then have that coupled to the sort of porous limit as in the Navier-Stokes, but in the flow we have this artificial sort of viscous resistance that we have to figure out, and that's detailed in these two papers here. Essentially, we then have just a pressure equation like this. So we have vastly reduced the number of degrees of freedom, and that makes that we can actually optimize some heat sinks in an hour using 100 cores, and using 20 it'll take around 5 hours. So this is much more realistic in an industrial context. So the question is now, can we extend this from just a single component, so there's a single cooler for a single electronics chip or a single LED package, to a full electronics cabinet? And that's what I've tried to do in my ITherm paper here. So generally we have these very complex interactions. So I'm looking at vertical electronics cabinets that are common in telecommunications. So we have multiple electronics chips placed in our cabinet. We have complex interactions between these various components. And the question is, are standard heat sinks sufficient? And more importantly, should every heatsink be of the same type or the same geometry? So I've set up this simple problem here. So we have 4 equal sized chips. They're 1 watt. We have the green here is where we can place material. We have flow coming in here, or rather can be sucked in here and expelled here. So we are looking at only passive natural convection here. So again, we introduce this approximate model and we can optimize this problem. We see that the optimized heat sinks are mostly pin fins. They're mostly straight. Some of them are a little bit curved, and we get an even distribution of material between the 4 heat sinks. So each heat sink uses approximately the same volume, and we have a global volume limit here. But if we look at the flow using the approximate model, so this potential-like flow model, we get a very even distribution of the flow, and largest velocities are in between the members. So we see that the flow is very easily distributed among the four. And if we then try to post-evaluate this design using Navier-Stokes, we see that this is just not the case in reality. We have inertia is very dominant, and actually the largest velocities are through this diagonal from inlet to outlet. So these two heat sinks don't see a lot of cold air. So we see that the cold air is not distributed well in the full model, but of course when optimizing using the simplified model, it doesn't see that. If we then optimize using the full model, we get these elongated fins, these elongated cross sections again. They are curved to accommodate the flow, and we see that we have more material away from the main flow. So these two diagonal ones here that are off the main flow diagonal have more solid material, and that's because the convection is of a lesser degree. Then it's better to use some conductive material. If we compare the performance in terms of the temperature of the heat sources, we can see that the Navier-Stokes optimized solutions perform significantly better than the ones using the approximate model. However, it is also significantly more expensive. So this is in terms of core hours. So let's say we have 100 cores. The approximate one would take 9 hours, but the other one would take 224, which is just under 10 days. Or I guess closer to 9 days. So the question is, can we do something in between these two by combining them in some way? So here we have the fully approximate model, the full Navier-Stokes solutions. But if we combine the two, so we first run with Navier-Stokes for a little bit and then the approximate model for the rest, we can significantly cut down the computational cost at only actually a better design performance here. The details are in the paper, but these numbers mean, so essentially when we have 6, we've run for a longer time. So here we have 1 and 5, and here we've only run for 2. That's why the performance is better. This is explained in the paper. If we run a little longer of the Navier-Stokes first before switching to the approximate model, we get a little bit better, but now at actually more cost than just running 2 Navier-Stokes. So the best is to start with the full model for a little bit and then switch to the approximate model rather than the other way around actually, which is common engineering practice. But what we see now here is we actually do get some of these characteristics from the full solutions in these pseudo-approximate solutions here. So what is the next step? How do we proceed to a larger flux or higher speed flows? Well, we need to capture the transient behavior, the unstable, the turbulent flow. Also, the fluctuating temperatures will be important for the given applications. For this, we need solvers and optimization algorithms for this. It's very expensive computationally, so it requires either high performance computing and or simplified models. So one of our papers recently shows that you can sort of approximate a 3D flow situation if you have these extruded type heatsink geometries, and you can simply have a 2-layer model that you can couple together. And using this, we showed an application for instantaneous cooling. So that is, we wanted the lowest temperature of this electronics chip after a very short time compared to steady state cooling. See some interesting differences in the designs here. These are much more aerodynamic. They have to last for a long time. Here it's more very fast behavior we're interested in. So the conclusions to round off are that topology optimization is a very viable method for heatsink design, but it does require supercomputers to use these full fidelity models currently. Simplified models, they render it plausible in an industrial timescale, but the accuracy is severely limited to certain cases. So for instance, this worked very well in an enclosure where just a single electronics chip, but where we have this full cabinet with several chips, it didn't work as well. Time-dependent problems, the computational time is the current bottleneck, so here we will probably have to use these simplified models, both in the physics and the geometry, in order to be able to treat them. And with that, I thank you and leave you with a list of references.